Thanks, thanks, Professor Mohammed. But it was challenging to see those innovations that you proposed, and I recognize some of them. And yes, indeed, we have to go this way to face our global water changes. But now we face another challenge, and that is that we now move from a physical presentation to a presentation by internet. So we have now two presentations. The first of Dr. Ragab Ragab. He is a president from the International Commission on Irrigation and Drainage, but at this moment he is also a research fellow at the Center of Ecology and Hydrology in the UK. And he will talk about the climate change impacts on water resources and possible adaptation and mitigation impacts. Professor Ragab, can you start your presentation?
Thank you very much, Mr. Chairman. Good morning, ladies and gentlemen. The global changes impact on water resources is really not only related to climate change, but also related to population and the land use changes, because they have also impact on water resources. Climate change impact, we use for that models developed by UK Hadley Center. And we had recently a study for 7 catchments from Scotland in the north to 4 catchment in the south. And these catchments, actually, we studied very much the impact of climate change on the water resources, surface and groundwater. I only would show one example from a Midland, close to Sheffield City, catchments called Don. And here you can see the climate change impact for the future, indicating there will be less surface water or stream or river water, especially in summer where irrigation is mostly needed. And also there will be a less groundwater recharge, also mostly in the summer as well. And this is actually also related as well to a possible increase in number of extreme drought events in the future, and the severity as well of the drought will expected to be increased. And also we looked at the gap between water supply and the demand in that catchment, and we found there is increasing gap between supply and the demand, not only in that catchment, but also in the other 6 catchments that we studied. At the same time, also we had some work in Brazil, Sicily, and Italy. And we found also in Cyprus, the gap is also widening with the future. The same thing for Italian catchments. Also, the gap is increasing between supply and demand. At the same time, it was also for Brazil. And when we looked at the impact of climate change on the communities here in the UK, especially farming and fisheries, they were interested to know especially what would be the change in the river flow and the depth actually of the water in the rivers, because they here in the UK, they have 2 types of fish, the trout and the salmon. And the trout would prefer its habitat to have a deeper water and a slower velocity compared to the salmon. And for that reason, we have to inform the fishermen community what's likely the future for the river flows and depths. And at the same time, also, we should show the farmers what's likely to be the situation with crop water requirements and the irrigation requirements, and the 2 indicators required by farmers in the UK, how much would be the soil moisture deficit and how much would be the actual evapotranspiration, for them to estimate what's likely to be the crop water requirements in the future. And now the impact of population on water resources is also similar to the impact of climate change. And if we look at the number of really population increasing from the 50s to 2020s, then you can see here there is increase in population, and that increase in population goes together with the increase on water withdrawal. And you can see here, according to the UN report 2021, there is a huge actually surge in the amount of water used over time, but because of the increase of population and water scarcity areas are also increasing from the 50s to 2050. A number of countries suffering from the water stress will be on the increase. Also, the impact of the land use changes here. And I will show one example here from a catchment that we studied. The measurements as well as the modeling indicates when you have a woodland, especially here in the south of that catchment here, when you have trees, you have less recharge. And when you have grass and arable lands, you have more recharge. And we looked at several catchments in the UK. This is one of them is the Froome catchment. And we can see if we add more trees, we actually reduce the flow in the rivers and the groundwater. And also if we increase the urban areas, we decrease the river flows and the groundwater recharge. And in particular interest, if we have more woodland, you expect less water to go to the river, and of course less water to go to the recharge because evapotranspiration rates from the trees are higher. And the other thing now is how can we adapt and mitigate these measures? And we have to increase the water supply and water use efficiency, better land management, suitable crops and crop rotations, use of water saving technologies, adoption of integrated water management, use of models as management tools. Increasing water supply can be done in several ways. You can harvest the rainfall from the clouds and using this cloud seeding technique. And currently in the UK, there's a new project where actually apply electric charge instead of using silver iodine. And you can also harvest the water. And this is example from South America, where also vertical mesh can be used. And we also tried here with a Spanish student to also harvest the dew water on films. And recently I came across, this is from Dubai Expo, where actually they have a solar system units, and it would also condense the water from the air, and can produce up to 80 liters per day. And rainfall harvesting can also be done at different scale on the roofs and smaller and larger catchments. And you can have it here runoff also harvested in mountain lakes, check dams, field ponds, and rural urban reservoirs are also examples. You can also hide the water under the ground, as Dr. Muhammad Dawood indicated, and this is artificial recharge through certain points. And I came across also the Brazilian way of harvesting water under the ground by having these digging trenches and putting sheets to isolate different sections, and the water, when it falls from the rain or the runoff, will remain within each section, as you can see here. And also use of saline water is another option, and we use that water to grow normal crops like tomato, the cherry tomatoes like this one in Malaga. Also, we had in one of the projects to look at the agro-industry wastewater, especially sugarcane industry and the beer industry, kingfisher in India. And we started to use that water and to purify the water and release that water to fish ponds. And these fish ponds actually can also help by taking the drainage water of the fish ponds and irrigate with, and that's another thing. And also we try to have a small scale community-based treated wastewater by a help of Danish companies called Grundfos, and where we can actually, for a small community, we can improve the quality of and treat the wastewater and for drip irrigation. And you can see the quality of the water is good enough for irrigation. Improving water use efficiency from the reservoir all the way to the field can also help to reduce the demand and gap with the supply. And also here in the UK, some farmers here, they put a floating solar panel to minimize the evapotranspiration, and also the low-level nozzles of sprinkler and center pivot that reduces the wind and evapotranspiration losses. And also we use the partial root drying method by using twin drip irrigation. The plant is in the middle and two drip lines. We only allow one drip line to operate at a time, and the next irrigation the other one. So we irrigate only half of the root zone, and by this we save 26% of the water compared to conventional drip irrigation, and 40% of water when we use sprinkler irrigation. There is also another thing that here from India, through the ICID work, where we irrigated rice by drip irrigation, and we can save 52% of the power, and we save 66% of the water. And also, there is now a new innovation about nano irrigation, where the water is released continuously with a small amount, and we can save a lot of water, and that's the efficiency also can go up to 95% compared to the surface irrigation. And also there is a new system here, it's called ultra low flow drip irrigation system, where actually you confine the water to only the root zone compared to the conventional drip irrigation, where you can have some losses. And the flow here is too small, between 0.1 to 0.3 liter per hour, compared to the conventional drip irrigation, which is almost 4 liters per hour. And also there's a new system here now is varying irrigation rates. So we don't irrigate with the same rate across the span of the center pivot. So the center pivot can actually give the exact amount to each area according to the need of each area or the crop that's grown under each part of the span. So you can see here, we are irrigating that part, but not this one. So you can irrigate according to the need. So you have a zone control and also speed control. The use of renewable energy, because we use energy to pump water for irrigation. And also this is example I showed before, that we can use that energy for farming activities. And also there is now floating actually wind turbines. And now it's widely used in north of Scotland here in the UK. And also to have renewable energy and the clean energy for agricultural use. And also you can use here the irrigation system using solar panel, and by this you have also clean energy. And this is also a small scale system for farmers to use solar energy to pump the water and also pump the water from wells. And also the biogas here is another thing, using the waste heat, food waste heat, to produce energy, and by this we can also mitigate the impact of the greenhouse. Water savings through accurate estimation of crop water requirements. We use this new technology, the Cosmos, for soil moisture measurements, and the scintillometry and eddy-covariance to calculate the actual evapotranspiration, which actually is the accurate estimate for crop water requirements. And we found actually from the measurements of the scintillometers and the eddy-covariance, we can actually have crop water requirements halved, 50% compared to the classical method of Penman-Monteith equation or FAO modified equation. So using the right technology, you might save up to 50% of water. And the Cosmos here of soil moisture integrated over areas 300 to 700 meters radius can also be used as a continuous measurements and also can give you an indication about soil moisture deficit. If it's green, you don't need to irrigate. If it's yellow or amber, it means just mild stress. If it's red, you need to irrigate. So this new technology also, you can have it to map the soil moisture and soil moisture deficit across the field. And that's really so many ways that you can mitigate and adapt for the climate change. And thank you very much for